I'm here to talk to you about designing and building a language. Now, if you read the abstract, you may have been under the impression, as I was when I wrote it, that I was going to sort of walk you through the process of designing and actually building the language. And that was the original talk that I wrote. But I started talking to people about it, and I kept getting a couple of really common questions. Like, why would you ever make a language? There are so many languages already. Just use one of those, right? And then there was another set of people who kind of were in the know a little bit, and they knew that I had actually implemented a language at work. And they asked me a different kind of question, which is, how did you convince them to let you write a language at work? And so I kind of hope to answer all of these questions as part of this talk. We are going to go through a little bit of design and actual implementation, but I want to leave the possibilities really open for you to experiment with your own stuff. So, oh, yes, so I've renamed the talk, by the way, to How to Tell When You've Accidentally Written a Language and What to Do About It. And so I hope to also give you the secrets to this. So here's the agenda. First, we're going to kind of deconstruct what we think of as a computer language and what it means to implement one. I'm going to do a little bit of an aside about data-driven architecture. And then we're going to talk through the design process and the actual implementation process. So I hope by the end that you are motivated and know how to start going about trying to do your own language. So first, what is a language? If you go to any bookstore or library and pick up a copy of one of the popular programming languages books, say like the Dragon book or the Tiger book, or you go to any kind of like internet tutorial, you'll find kind of the following outline for how to write a programming language, right? You're going to start by being told how to use Lex and Yak and maybe Bison or one of the kind of things based on it. Or either that, or they're going to spend 5 chapters on abstract parsing theory and tell you how to roll your own Lawler parser and all sorts of stuff that you don't actually need to know. Then they're going to tell you about more stuff that you don't need to know, like single static assignment and control flow graphs, maybe continuation passing style, and they might, have a very strong opinion on the difference between the two. And then they're going to tell you how to emit machine code and machine code that pushes registers and jumps and works on your processor, right? These are how these tutorials and language books present it. And I think that this is really outdated, it's really restrictive, and it's kind of uncreative. And it's not wrong. Like if you did all of this stuff, you would have implemented a language. And there are several languages that do this. C does this, right? But it's really restrictive, right? So I want to kind of expand our notion of what it is to implement a language. So in order to do that, let's look at some modern languages. I'm going to start with Ruby, because Ruby is relatively straightforward. They take a string, they make it into a tree, and then they interpret it with some C code, right? And this is MRI. There are a bunch of other implementations of Ruby, right? So this is very straightforward. The pipeline is very small. There's a lot of complexity in here. And this is, in a lot of ways, an oversimplification. But it's pretty contained, right? Haskell has a much larger pipeline, right? You start with a string. You get a couple of different kinds of trees. You do type checking. And then they have this intermediate language called C++ that they use, which is sort of an off-the-shelf language, which is a subset of C with some nice features stripped out. Which you laugh, but that's actually what is appropriate for a machine writing code. And then it outputs native bytecode, and then it interprets it on your hardware, right? V8 is a popular implementation of JavaScript used in Node and in Chrome. And they actually have 3 different backends. So they take your string as an input, and so first of all, they can just evaluate that tree that they get from the string. They just interpret it straight. And then they can also run it in tracing mode, which generates this trace, and you have this nice graph of traces with a bunch of complex stuff in it. And from the trace, it can actually generate machine code. So usually in your browser, all 3 of these are happening at the same time, depending on whether the code is considered hot. Data log is one of my recent favorites. It's what you will use if you're using Datomic. It's interesting because its input is not actually a string, unlike a lot of the other languages that we've looked at. Its input is a data structure. You can express it in Fresian, or you can just use Clojure data structures, right? So your code is a data structure. And Clojure script, I'm only putting in here because it uses a language intended for humans as an intermediate step, right? It outputs JavaScript. So in general, the only thing we can really say about languages, even these very large general purpose languages, is that they take something from a human, they do some processing on it, on some kind of tree, and then they interpret it, right? And this is what a language is. A language is a program that allows very complex human input to be understood by a computer. That's it. OK? So given that, here's a couple definitions. So this is a computer language. And I actually like calling them computer languages. Some people call them programming languages. It's not necessarily the case that your users will be programming with your language. So I generally call it a computer language to emphasize that it's being interpreted by a computer, right? So that's a computer language, human-controlled input of unbounded complexity. An intermediate representation, which is called an IR, is a bit of jargon, but all it is just one of the steps in the middle of your pipeline. Usually, you can actually dump it and view it as a human, so you can get kind of an insight into what's happening. A parser turns text into data structures, and code is just any input to a computer language, right? This is all pretty simple. So given that, let's talk about data-driven architecture. So data-driven architecture is this new fad where you are supposed to design your systems around data, right? You sort of push it to configuration in a way. So you take this data that's maybe written by a human, and your application takes that data and uses that data to specify behaviors, right? So it gets kind of interpreted in a way, right? And that data can be potentially very complex, depending on the application that you're using. So let's look at some of the disciplines that you would need to implement a data-driven system, right? Some questions you might want to ask yourself. If the data gets persisted, what's the migration strategy? If you change the format, how do you get from one to the other? Or are you locked into a format, right? Who provides the data? How's it composed? How is it stored? Is it in a Git repository? Is it in a database? Is it in the cloud? I don't know. Is the data for humans to write, or is it generated by machines? This is a very important question that we need to ask ourselves. And I see a lot of people forget this and write, for example, configuration data structures that are way too large and unwieldy for actual humans to interact with. What behaviors or resources do you want users to be able to specify with your data? And what kind of behaviors and resources do you want to exclude? And this isn't necessarily taking away power. It's more giving guarantees in a way. And I'll talk more about that. So when I hear people talk about this, as a language designer, it's really familiar because the disciplines that you need when you're designing a language for people to use are exactly the same, right? And I don't think it should be very revolutionary here to tell you that data is code, data is code, right? Every single one of these is something that you have to think about when you're understanding how to build a computer language. Now, if you're building sort of a general purpose language for what we consider to be programmers, a lot of these questions are answered already, right? We have source control, we have, of course it's intended for a human, right? Although someone else might decide to generate it for us. And we do have to think about what kind of things we want users to be able to do and what kind of things we want them not to be able to do. You may have heard of Greenspun's 10th rule. If you haven't, this is how it goes. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. And there's also Morris's corollary, which says including Common Lisp. And I'm not sure if that means Common Lisp programs or the Common Lisp project itself. Either way. And it's very tongue-in-cheek, but Greenspun said this for a reason, right? We keep writing these systems that actually accidentally contain languages. And I actually think that this quote gives way too much credit to C, Fortran, and Common Lisp. So my slight edit is that if your user input is sufficiently complex, then your program is likely to contain a computer language input, which is probably not very well thought out. So let's look at some examples of this, right? One very common source of accidental languages is XML and JSON. And XML and JSON are very convenient because they can describe arbitrary trees. And when they can describe arbitrary trees, suddenly your user input starts to get very large. And the sort of canonical example of this is Ant. Ant, who here has built a project with Ant? There's got to be some Java people here. Yeah. So Ant was intended as a configuration syntax. And then they added conditionals. And then they added let binding. And at a certain point, it became a full language that now we have to reckon with an entire language whose syntax is XML. Cold Fusion is different because it was intended as a language, but they decided that parsing was too hard, so they wrote everything in XML, right? Query parameters for complex HTTP interfaces. You're not supposed to be able to nest query parameters, but I've seen some people try. Watch out here. Consider your entire HTTP interface as a whole, and think about how the user input might be expanding uncontrollably, and how you might factor some of that out into a language, right? This almost happened to Neo4j, actually, until they backed off and wrote their Cypher query language, which is quite nice. PHP is one of my personal favorite examples of this. PHP was intended to be a set of kind of ad hoc scripts to make your personal homepage. And sort of unfortunately at the time, it was in a niche that was a bit bigger than its boots. And so being the only dynamic language that was open source that you could deploy that easily. So it kind of got things globbed onto it until it was like an actual language to be reckoned with. And they've dealt with some of their problems, but they still have to deal with this history. I love harping on Viml. You may notice that I'm using Vim, and the software that is driving the presentation is written in Viml. This was a language tacked onto a language that was already tacked onto another language, which was really meant to be a user interface that you communicate back and forth in to do text editing on a line because it was too expensive to render the whole file to the screen. Who here has ever read the man page to find? OK, great. Hidden within the flags of find is a very simple logic language. It's not, it won't like do goals and that kind of stuff for you, but it's got and or and not, and you can group things. It's quite sophisticated. And it's expressed in terms of command line flags, which is pretty great. OK, so if you have this kind of system and you understand that you're going to have very complex user input, you probably want to think about using some programming language concepts in your implementation, right? In your design, especially. So how are you supposed to do that, right? If these projects had sat down and been able to understand what they were doing and how they were going to end up, what might they have done differently? So let's design a language. Now, languages are very diverse. They have all sorts of different kinds of implementations, from very, very large to very, very small. But I think generally they break out into about 4 different categories. Some of them don't have parts of these, and some of them have parts of these that are very large. But generally, you have the front end, which is the part that connects to the human, right? This is the part that you interact with. You have the back end, which is the part that allows the computer to do stuff. You have translation, which is the process of getting the user format to the computer format. And then you have runtime, which is sort of supporting code to allow the computer to do the computer format part. And I'll get into more of how these kind of interrelate. But again, some of these can be very large and some of them can be very small. Really depends on what you're doing, right? So the goals for your design are to get, A, the computer to understand the human, right? You want code that is written to be able to be interpreted, right? This is the very basic, like, let's implement it, right? You also want to make sure the human interacting with your system understands the way in which the computer understands their code. And this is so that I can go and read something else that someone else has written and understand what the computer is doing with it. Otherwise, we end up with write-only languages, right? Also, I want to understand, if I have a new idea in my head of what I want to do, I want to understand how to get the computer to understand that, right? If that's within the domain of what your program's supposed to do. Cool? So these are all rather independent and all very important design considerations. So questions you should ask yourself when you are designing a front end for a language. How will your users write, store, update, and run code? This is pretty straightforward if your language is in text and you're intending people to write things in a text editor and put them in a source control system. It's a lot less straightforward if it's embedded in a system or your input is data structures or query parameters. Sometimes users don't persist code, like for command line languages. They'll write it and press enter, and it'll run, and it's gone, right? What kind of errors can happen, and how will they be reported? Errors are not an exceptional case in language land. They are the bread and butter of how your language is going to interact with the world. I see so many people writing languages and thinking of the error cases as kind of like, well, I guess they messed up, so I don't know. Error cases in languages are first class. You need to make them happen. And they need to be nice. Clojure, excuse me. How much power do your users need, and how much reliability do they need? This is a trade-off that you may find yourself having to make a lot. Do you want to give users the power to confuse other users? This is a hard question, because sometimes the users need that power. Sometimes for your system, like C as a language, for example, people need the power to do pointer arithmetic, right, in that domain. It results in a lack of reliability, because I, as a user of a C library, don't know what that library is going to do at all. I have no guarantees about it other than what's in their documentation. And And this isn't necessarily a question of possible and impossible. It's way more a question of easy and difficult. What do your users expect to be easy, and what are they okay with being difficult? What do you want to be easy for them? And what do you want to be difficult for them? It's okay to make something difficult if it's something that really they shouldn't be doing, right? The core of all of this is you need to understand your users, right? This is what I keep repeating. And it's something that people don't really think about as much. They think of languages as a very kind of low-level technical project. And it actually is much more about UX and understanding your users' experiences. Things to try in this phase, I would suggest writing a highlighting mode for your editor if you're using text, and mock-up code. This allows you to really quickly figure out what you kind of want to do and generate ideas. Once you've generated ideas, you want to kind of pick a complex task that your users have and implement it in mock-up. You want to show it to people, especially your target users. These are all basic design principles, right, of how you design for users. You need to reconsider everything. You are going to discover that you are wrong about a lot of things that your users want. And as in languages that I've designed, I've had to kill so many features that I really loved in order to actually make it work for people. So be prepared to kill features that you love. It's OK. And in general, in the design process, you want the feedback loop to be really small. You want to be able to try something, get feedback on it, and iterate on it. And the larger that is, the harder it's going to be to whittle that down to something that's really nice and is going to meet your users' needs. So for the back end, in planning for a back end, I suggest that at first you start with something easy, and that you limit the language's access to primitive features so that you can swap out backends later. Unless the backend is a very, very important part of what you're doing, it's pretty advantageous to do this. The language that I wrote for work has had 5 backends now. It had 3 ways of interpreting, one where it generated JavaScript, and one now where it generates Ruby, which is fun. You generally want to aim to get the really big picture performance stuff right. Generally kind of, big O notation kind of performance stuff. Things that block and things that don't, like the sort of big picture stuff. Don't worry too much about like how fast your bit operations are at the beginning, because you can fix a lot of that stuff later. So at this point, I want to talk about the abstraction gap. So here's your language. There's a human at the left and interpretation happening over there on the right. And the distance between the format that the humans are reasoning about the code in and the environment in which it's interpreted, I call the abstraction gap. Now, the abstraction gap, the bigger your abstraction gap is, the more work you're going to have to do, just in general. But there's a couple of pressures that keep applying to this gap. One is that the higher level the user's stuff is, the better the UX is, right? The more control you can have over their error messages, the higher level concepts that they can reason about. And then the lower your interpretation context is, the better your performance is going to be in general. Writing an interpreter in a high-level language is going to be a lot slower than compiling it to run natively on your hardware, right? So there's these pressures kind of pulling this gap apart. And there's a third pressure that says the bigger your abstraction gap is, the more translation you have to do, and in general, the more runtime support you're going to have. Runtime support could include garbage collection. It could include, for example, there was a data system, which I think of as a language that was presented at ClojureConf last year, where you just make a data structure and a web service pops up. And all of the code that actually runs an HTTP service is runtime support, right? And you have to have a very complex set of runtime support to make that happen. So depending on what you're doing and where your domain is, you may want to make very different trade-offs in these cases. So these are the three things that you'll have to trade off between: is high-level features, fast interpretation, and slim runtime support. Cool? So understand where you are in that in those trade-offs. All right, so when you get down to implementing a language, and I'm assuming that you're in Clojure now, you can implement in all sorts of different platforms, but I want to talk specifically about some Clojure techniques that you might want to use. For the front end, you need to decide what the input format is. The goal in all of your input formats is to get it into this variant format. And if you saw my talk at ClojureCon, this will be familiar. Otherwise, just think of it as an arbitrarily nested vector thing with keywords at the beginning telling you what kind of thing it is. And those keywords are specific to your application, so you get to decide what they are and match against them later. So one possibility is that your input is text. This is very common. If your input is text, use instaparse. It's very unlikely that you're doing anything that it can't handle. I don't want to spend too much time on this because, like I said, all of the books spend 5 chapters on it and don't really get to anything else. So just use instaparse. We're done. This is the easy part. Since we're in a Lisp, another option for input is quoted forms. And you see a lot of languages like this. Herbert, there's, well, Hiccup isn't quite quoted, but it's, in a sense, a language. And a lot of macros end up being basically small languages, right? You can just do quoted forms manually. You can just get the forms and destructure them and do whatever you want. If you want kind of a nicer interface, there's this syntax rules library that they have documentation. Go read it. And it's quite nice. So to get your user input interpreted, there's a couple of options. One is just to walk the tree and do stuff. And what you're going to use here is Clojure core match. And that's capable of destructuring all of these vectors within vectors and making stuff happen. You might also consider outputting Clojure. Clojure is really good at this. I have written a language that outputs Clojure, and it's a surprisingly good interface for this. At the time that I wrote it, Clojure core match had a bug with loop that made the whole JVM go into an infinite loop when I tried to load the file, but when it tried to macro expand. But it's a lot better now, and you should use it. OK, now for translation. And this is the hard part. And I think a lot of the time, because of the way that languages are presented, people think of parsing as the hard part, because you're taking a flat thing and making it into a nested thing. But honestly, it's 2015. Parsing is the easy part. If you get to design the syntax, parsing is very straightforward. The hard part is translation from your input format to your output format. The goals are to validate the code, if applicable. And I suggest you go on YouTube, if you didn't see it already, Nathan Sorensen's talk on domain-specific type systems. This is a very deep topic about how to validate code and sort of decide if it does what it's supposed to do. And then get your code from the syntax to the target. There's no library that you can plug in here. This is whatever it takes programming, right? You just need to make it happen. And basically, the main strategy that you're going to use is you're going to destructure this stuff with core match and create new trees, right? A couple of tips here. Do not shy away from using mutable data structures if they're sort of confined to one step of the process. They're really useful, and if it makes you feel any better, Haskell's compiler uses mutable structures everywhere. So it's OK. If you find something getting to be a bit too complicated, you can introduce a new intermediate representation. This is a strategy that I've used a number of times, and it really it often does a good job of separating one part of the process from another, right? You can stretch out the pipeline if you need to. Another thing you might do, instead of creating a new tree format, you might just do iterative steps on a single tree. These are all things that are used a lot and that I've used successfully in the past. At this point, when you start doing translation, you will pick the back end, you will write your parser, and then you will start trying to get from one thing to the other, and you will realize that things in your design are impossible. It's okay. This will happen to you maybe 3 or 4 times, depending on what you're doing. And it's okay to just loop back to design here and say, well, I need to change these things, and show it to your users and go through that process again. So things to take away. One is, don't be afraid to write languages. They're as easy or as hard as you make them. The hard part is that your user input is complicated, and you need to do the work to interpret it. And that's essential complexity, not incidental. Learn to understand when a language is an appropriate solution. If your user input is arbitrarily complex, then you probably have a language on your hands. Treat your data like your code like your data. Understand where it comes from, where it goes, how it's stored. But mostly, and this is the big takeaway I want you to get here, is to understand your users. This is the #1 thing that we need to do as programmers that we are currently failing at in a lot of our language implementations. So take the time, talk to people who are going to be using it, and really put yourself in the shoes of people who are going to be using your system. So that's what I've got. Questions? Yes?
So you said a lot of stuff about, or how important it is to understand users, but not very much about how important it is to understand the problem domain in which your language is designed to operate. Can you talk something about that?
So the question was about understanding the problem domain, in addition to understanding users, understanding the problem domain in which your language is supposed to operate. And I consider that part of it, right? Like your users are wanting to operate in a particular problem domain, and you need to understand that domain. You need to understand the language that they're going to use to talk about the problem domain. You need to understand the limitations of that and really kind of know what you're doing. Anything else? In the back somewhere?
Up on the balcony.
On the balcony. Excuse me.
Do you have any code that you would like to point us to for stuff that you've done?
So a lot of the stuff that I've done is not open source, unfortunately, especially the one that I've written for work. I've done a number of designs, which you'll find on my blog, which is there. My latest project is called Tulip, and it's a general purpose language. I'm not done implementing it. I'm sort of in the middle of having started the implementation process and looping back to design, having found some of the things I wanted to do are impossible. But that's kind of where it is. Yes, here.
What's the domain where you were making the language at work? Like, was it a need for programmability in your system, or
we have a large science team, and they're not necessarily going to pick up Python to do their work, and they needed to be able to define certain rating rules and how certain things got rated. And at the time, we already had a system that was a tree of nodes that would roll up values, and if you squinted and turned your head, it was a language. Yeah. There was a question over here.
Oh, no, I was pointing.
Oh, you were pointing. Okay. All right. Well, thank you very much.